Okay, good morning. As Ed say, I am going to present fundamentals, problem in combustion. You know, I will not discuss applied things. I stay at the level of fundamentals. So I will develop different analysis and in connection with laboratory experiments. That's a very important point. So I am from Aix-Marseille. Now I am Professeur Emeritus. Now I am, because I am getting old. So, but you see, where is Aix-Marseille? Is in south of France, and it is a nice country to. If you have the occasion to visit this part of Europe, it is worthwhile. I am, you know, my whole goal is to provide you with understanding of various complex phenomena concerning flames and detonation. And the best way in this direction is, in fact, to develop analytical solutions of well-posed mathematical problems. It turns out that you cannot do that with basic equations on fluid mechanics because they are too complicated and there is no possibility to develop analytical solution. You have still the possibility to develop numerical solution. That's true, especially now because the computer are so powerful. But it turns out that in order to understand what does mean understanding in fact, this is one of the problem, a question which is not so clear. The answer is not so clear. For me, understanding is to have an analytical solution of a problem. In fact, this is not new, you know, from Newton did that in the 3 centuries ago. But now, you know, this kind of thinking is less and less developed now. This is very strange, but it is like that. So I will try to pick you back, to bring you back to this spirit, you know. It turns out that you cannot do that with general equations. So the first step, and it is a difficult step, is to reduce the problem by using approximations, well-controlled approximations, and in such a way that the key is to compare with experiments. As soon as you have a model with analytical results, this is the capability of the model, or the interest of the model, is if you are able to reproduce experiments. If you are not able to reproduce experiment, throw that to the basket, it's nothing. But so this is a difficult part, because how to reduce the problem? And this, as I told you, you need some approximations. And these approximations, you need to have a good insight into the physics of the problem. And this is not so easy. And then you use analysis, let's say dimensional analysis, to reduce the problem. So I am going to present to you, I made the choice this year to cover a large spectrum of topics. And I cannot go into the details of each topic. So I will develop the complete analysis in few of them, not in all of them, because of lack of time. I cannot do that. But every time I will try to give you an overview of the methods and the physics of the problem. This is what I am trying to do. You see, I will not follow exactly this lecture like that. The two first days, I will develop 1, 2, 3, 4, 5, and 6. And then the third day, I am skipping to supersonic waves and detonations. This is because there are a lot, you know, the transition, the deflagration to detonation transitions is one of the most fascinating problems in science, and especially in combustion science. And I have to say that the problem was not clear, and I think that now, since 2 years ago, we made a real improvement in the understanding of this problem, and I want to present this part. And so this is why I will skip. The third day, I will look to this problem. Okay. Let's begin by order of magnitude analysis. Every time you have to start by order of magnitude analysis, not only to reduce the problem, but also to have to get a good physical insight into. Let me remind quickly what combustion here is. It is a chemical, let's say, reactants that are transformed into products with heat release. And the heat release is coming from the binding energy of the molecule. And this binding energy is typically a few electron volts. So when you take this binding energy, you obtain something like, for the temperature, an increase of temperature around 2000 K. You know, a few electron volts is equivalent to 2000 K when you say, well, okay. This, then simple look show you what is going, what the temperature is going to be. Another point, very important point in combustion is the extremely sensitivity of the reaction rate to the temperature. Below 500 Kelvin, the mixture is completely frozen. But at the temperature of the order of, that doesn't work, okay. At the order of the heat, of the maximum temperature, the reaction rate is about 10 minus 6 seconds. You know, this is the main characteristic of combustion, the high thermal sensitivity of the reaction rate. And this high sensitivity to the of the reaction rate is responsible of two things. First, that you may have abrupt transition in the different regime of combustion. This is because of this high activation energy. What you can have also is a quenching mechanism. It's easy to quench a flame. You know, you just have to take out a little bit amount of energy and the flame can no more propagate. This is, and finally, another point is that because of this high sensitivity of the energy, of the reaction rate, the combustion proceeds through the propagation of flame. Combustion proceeds through the propagation of, let's say, discontinuity between unburned and burned mixture. Let's say we call that combustion waves. The first combustion waves, which was identified clearly at the beginning of the 18th century, was the flame. And the flame is wave propagating between 10 centimeters per second to 10 meters per second. 10 meters are the most reactive mixture that you can have. Let's say it's hydrogen, oxygen at ordinary condition, or acetylene oxygen also is close to 10 meters per second. And an important point is that the pressure jump is nothing. You may completely neglect the pressure in this wave. In the at the same, a little bit later, it was the detonation was discovered. It was a supersonic waves propagating the combustion at a speed about 2,000 meters per second in the ordinary condition. It is and this process, which is this wave, which is supersonic wave, has also a very important jump in pressure. And this is why these waves are so destructive. You know, they are excessively dangerous. In between, you have fast deflagration. And this is due to turbulence propagation. And this turbulence propagation, let's say, could be around, the speed could be around 100 meters per second. But you have still, you know, the difference with the detonation is that not only the speed, which is still subsonic, but the pressure, the jump of pressure, you have a decrease of the pressure, which is small, but not as large as the increase of pressure that you have in detonation. So here are the picture of some of the most famous scientists in combustion science during the 18th and the 19th and the 20th century. You know, one of the basic elements to understand flames and detonations are the kinetic theory of gas, which was developed during the 19th century. And this elementary kinetic of gas, you have to keep in mind only a few things. That first, you have a mean velocity of the molecules. That's one point. And this velocity is nearly the sound speed. That you have to keep that in mind. That at ordinary pressure here, here in this room, the velocity of the molecule are around 300 meters per second. That's about that. So you have a velocity, you have collisions, and this collision between molecules are separated by a distance which is called mean free path. This is a microscopic length, very, very small length. I will give you some order of magnitude later. And you have a time, which is a time between two collisions. And this time is related to the mean free path and to the velocity, velocity of the molecules, which is associated to the temperature, in fact. The important point is that with this basic kinetic theory of gases, you develop what is called the Maxwell-Boltzmann distribution, telling you how the velocities of the molecule are distributed. And another very important point of this kinetic theory of gases is that the molecular diffusions, you know, when you have, for example, a black molecule in white molecule, put that separate in a box, and you liberate, and then they diffuse each one into other, and they become gray. And this is due to the molecular diffusion, which is a random walk. And this random walk, this is a famous result of the beginning of the century, in fact, last century, excuse me. is that if you have a spot of white molecule in black molecule, let's say milk in coffee, you have a spot. How the spot is spreading, here you have the result. There's a spreading like, you know, it's controlled by the molecular diffusion, D, which is this diffusion coefficient, which is related to the microscopic quantities controlling the kinetic theory of gases, which is this diffusion coefficient is simply, you can write that in two, that I will use in the following, that you can, you know, the dimension of the diffusion coefficient is the length square divided by the time. And because of the kinetic theory of gas, you can show that the diffusion in a gas is the mean free path square divided by the time between collision, or same way, it can be written as the square of the sound speed multiplied by the collision between molecules. So these are important things to keep in mind if you want to have a good idea of order of magnitude of the phenomena that you are looking at. Now, with simple dimensional argument, you will find directly some interesting result. You know, what are the parameters? You have a chemical energy per unit mass. This is one parameter. And this parameter, QM, tells you that the temperature, the ratio of temperature between unburned and burned gas is between 5 and 10. That's because of this binding energy of molecule. Now you have sound speed. The sound speed does not vary so much with the temperature. You know, it's like, it varies like the square root of the ratio of the temperature. So it's not very important. So you have a speed, you have a reaction rate, and with this you are building molecular and thermal diffusion coefficients. Now, looking just to the dimensional analysis and considering and recalling that the heat release per unit mass is just a velocity square, you know? This is heat release per unit mass is just a velocity square. Now, if you take the square root of the velocity square, you have a velocity. What is it? This velocity is about the sound speed in the burned gas. So it's about 1,000 meters per second. That's all. And this is exactly the order of magnitude that you have for a detonation. It comes from that, the order of magnitude. But on the other hand, you can build a velocity using the diffusion coefficient and the time, characteristic time, between collision between molecules. This is what you can do. And the only way to have a velocity with this diffusion coefficient is to take the square root of the diffusion coefficient divided by the reaction time of the combustion. And this, if you do that, you obtain something of 1 meter per second, which is typically the velocity of a flame. So just by a dimensional analysis, you find out two possible waves, two possible velocities that are quite different. Now, a better insight now into the problem is obtained when you consider that the combustion proceeds through inelastic collisions, where you have first, you have molecules of reactants that collide. It's not so simple, but it is a good idea. And then they collide, they are broken, and atoms, ions, and so on, recombine into two products. Okay? So before to go from, in order to go from a reactant to a product in combustion, you have first to break this reactants, this molecule. So you need energy for that. And hopefully you are gaining more energy when you recombine these things. But first you have you have first to pay this price. Okay? And this gives you the activation energy, which is the energy necessary to break this molecule. And it turns out that this energy is, this energy E, activation energy, is about 8 to 10 of the kinetic energy. So the ratio E divided by KB is a constant, Boltzmann constant, TB is the temperature of burn gas, is about 8. And you see, as you see, hopefully you are gaining some energy because the products are more stable than the reaction, so that the binding energy is stronger in the product. So you take this energy and you put this energy in the kinetic energy of the gas, and this gives you so now with this picture, a simple picture in mind, you obtain using the Maxwell-Boltzmann distribution, you can compute the number of inelastic collision per unit time and unit volume that are going to develop. And this is simply, when you do this calculation, it's a simple calculation, you find out that the reaction rate, which is the inverse of the reaction time, is strongly dependent on temperature, and it is, and you are, because of the Maxwell-Boltzmann distribution, where you have an exponential minus an energy divided by kBT, you obtain a term which is a reaction rate which is equal to the elastic collision rate, that is the number of collisions that you have, but not necessarily producing combustion because there are not strong, not energy enough, and this is called the collision, the frequency. 1/T call is called the frequency of collisions time an Arrhenius factor. You see, and this explains immediately why the reaction rate is so sensitive to the temperature. It is because this activation energy is large compared to the thermal energy. And when you develop, you make a small variation of the temperature, you have a large variation of the reaction rate because of this activation energy. Now, you develop the order of magnitude analysis, and you obtain that necessarily that you obtain using the Arrhenius factor, you obtain that the laminar flame speed divided by the sound speed is the square root of the Arrhenius factor. But this Arrhenius factor is very small. This is why a flame is markedly subsonic. That's for flame. Now you can compute also the thickness of this flame, and it turns out that the thickness is much larger than the mean free path. Once again, because of the inverse of the square root of the Arrhenius factor. And this explains that a flame can be, the flame structure can be analyzed by macroscopic equation, you know. You do not, it's not necessary to go to Boltzmann equation, because this will be terrible. It's complicated equation, nonlinear, very difficult to study. But because of that, because of this simple analysis, you conclude immediately that you can work out a theory for flame using macroscopic equations, the fluid mechanics equation, the reactive fluid mechanism equation. As you will see in my lecture, this is no longer the case for shock waves. Shock waves, I will discuss that later. So here is again, I have summarized here the main conclusion of this lecture. And it turns out that there are this limit, that the simple dimensional analysis, very simple, you cannot imagine a simpler theory to understand flame. This is the simplest one. The problem is that when you do that, okay, the order of magnitude are good, but not the value themselves. You see, for example, typically you are going to find a flame velocity which is 10 meters per second. This is okay for hydrogen oxygen, but it doesn't work at all for hydrocarbon air flames. Hydrocarbon air flames are between 10 and 25 centimeters per second, so it doesn't work. And also the flame thickness that you obtain is too small. This tells you that you need a better theory to describe this, to describe a flame. Here I have plotted the flame velocity, methane air flame, with the equivalence ratio for different experiments. And you see, typically you have something between 10 and 35 centimeters per second, depending on the equivalence ratio, because the equivalence ratio is going to control the flame temperature. That's clear. So you change, if you change the flame temperature, you change the Arrhenius factor, so you change the flame velocity. Here, near the flame, I have a plot here, the flame structure of it's in a lean methane flame, and it is for very close to the flammability limit, such a way that the flame velocity is small, and the flame velocity being small, the flame thickness is large, so you can enter into the detail more easily in numerics here. This is easy to do now with numerics. However, flames are fronts, planar fronts that are unstable. They do not, in principle, without, if you do not do anything particular, this flame cannot stay planar. Okay, and here I have give you what just a representation or mechanical representation of what is an unstable problem. You have in the middle, this is unstable, and on your right, you have a metastable solution in mechanics. That this, you know, you just the state is stable except if you perturb the solution with a sufficiently large amplitude of distribution. So in that case, you go above the bump and then, hop, you're unstable. Okay, this is a simple representation. Okay, there are mainly two intrinsic mechanisms of instability of flame. The first one, I will explain you that in detail in the lecture, not the first one, but later. The first one is due to the change of density, because, you know, if the flame is isobaric, P is the same, pressure is the same on both sides. Pressure is rho T, is density times the temperature with a factor doesn't matter. I don't care. So that the density, if the pressure is constant, the ratio of density is the inverse of the ratio of temperature. So you have a strong change of density across a flame. A flow, so a flame has to be seen like a front separating two gas with a different density. And this is going to produce large cells that you have that are shown here for propane lean flame. And you see in this flame you have cusps. Clearly you have the cusp. And these cusps are very easy to understand by an optical analogy, which is a Huygens construction. If you take a curved surface, okay, and you say, okay, this curved surface is going to propagate with a normal constant velocity, you are going to produce in finite time cusps. You know, that's immediately, you see. You can see that immediately. There is a second instability, which is thermodiffusive, which has nothing to do with hydrodynamics, which has to do with the diffusion coefficient, the diffusion of species that are different from the diffusion of heat, you know. And this is going to produce, this occur in propane-rich flame. This is going to be produced when the molecular diffusion of the limiting species is larger than the thermal diffusivity of the mixture. And I will explain that in detail later on. So there are other types of instability when you consider combustion in a cavity. The coupling of flames with acoustic modes of the cavity is typically unstable. I will explain you that later. This only at the end of the session. And this is called the thermo-acoustic instability, which is a nightmare of the engineer building rockets. That was a terrible difficulty to avoid this kind of instability, which is strongly destructive. So this instability is not an intrinsic stability of flame, of the structure itself, is due to the interaction of the structure with the acoustical mode of the cavity. Now I will show you an illustration of the, okay, this, you look at this experiment. First, you do not have the sound. Oh my goodness. I will try to put the sound. Okay, I stop this. Okay, back. I'll try it because the sound is very impressive. First experiment, you have a tube, a methane air flame, with a velocity of 33 centimeters per second. That's the first experiment. Okay. Okay. Okay, this is the first experiment. Did you hear something? Okay, now listen. Now you change the small, you know. You see? And this is a typical instability coming from the coupling of the longitudinal acoustic modes and the flame structure. I will explain that in detail. Because now here you have a cut by laser cut of the flame front, and you see the oscillation that you see is the acoustics that are, you know, and as the amplitude of the oscillation increase, the flame structure break off, and this is a noise that you have here. So this is also a phenomenon that I would like just to give you some idea. Okay, this experiment I showed to you is 20 years old. Now people are again doing experiments the last year. I have reproduced here an experiment of 2018, but there are even more recent experiments. The flame is very sensitive to acceleration. Let's say constant acceleration. The Earth of gravity is the constant accelerations that you have on Earth. When the flame propagates upstairs in a tube, it takes the form of a bubble. okay? When you are if you are a good experimentalist, it's not easy to do. And if you now deal with a flame with a small flame velocity, about 10 centimeters per second, when you propagate downwards, the flame is completely stable. As planar is completely stable. This experiment that have been developed 20 years ago in Marseille, or 25. Now you increase a little bit the velocity, and you reduce the experiment, and what you see, cellular structure appearing on the flame. All right? Now, another very interesting effect that is not well understood, by the way, is the following. You have a Bunsen burner at the exit of a tube, okay? And it is a rich flame. What you see, the cone you see, this is a premixed flame, and the light you have on the side is a diffusion flame because you have an excess of hydrocarbon in the burn gas that is burning with the oxygen of ambient air. So this is, so you have, so focus your attention to the Bunsen flame, not to the premixed flame. Now, you excite the acoustic mode of the tube, and you will change a drastic, you will see a drastic change in the flame surface. It turns out that I did work on that problem with my colleague Guy Joulin 10 years ago, maybe 15, and we did not succeed to explain clearly this phenomena. And what is clear is that it looks like that the flame shape is close to the equipotential, to one of the equipotential of the acoustic emitted from the gas. But this is not well understood for the moment. In fact, I gave up to try to understand that. We gave up. With Guy Joulin, we gave up. And, okay, let's now go to the second lecture, which become a little bit more, let's say, technical. Let me recall you what you must know, I guess, or at least you think you know, are the basic equations of the reacting fluid mechanics. The presentation I'm going to give to you is not original. It's, it's an old topic, but you will not find such a presentation in most of the book. The first point is the following, is that a gaseous mixture in normal condition can be approximated by a continuum medium in local equilibrium. This is because many molecules, microscopic molecules, are concerned in each fluid molecule. A fluid molecule is represented by a point, but inside this small volume, you have a lot of molecules. And because of that, you have a continuous, the medium looks continuous. Because the mean-free path, that is the distance between two collisions, is infinitely small compared to the size of the small size of the point, macroscopic point that you are looking at. So this is, and another important point is that the relaxation time towards equilibrium of a fluid particle, to obtain the Maxwell-Boltzmann distribution is very, very small compared to the characteristic time of evolution of the macroscopic variables that you are looking at and you are studying in laboratory. Just a point, you have to be careful with shock waves, because this is no more the case. the thickness of a shock wave, when the shock is about Mach number around 3 or to 6, is microscopic. It's few mean free paths. So you cannot use macroscopic equation. You should be back to Boltzmann equation, which is a terrible, which is not easy to do. Let me begin by defining what is a conserved extensive quantities. We call an extensive quantity a quantity which can be represented in any volume by an integral, volume integral. Okay? And this volume integral, you have the density, mass density of the quantity, which is small a, and the mass density, which is rho. And you integrate that to have the value of the extensive quantity, which is associated with the velocity v, capital V. When you take the derivative in time of this quantity, extensive quantity, you have two ways to change this quantity. The first thing to do, the first thing is that you have the time derivative is separated in two parts, time derivative 1 plus time derivative 2, and the time derivative 1 is just, corresponds just to the flux of this quantity around the boundary of the velocity of the volume. You know, you have a flux. So, for example, in this room, if you have people enter for some doors and getting out from other doors, the difference of the flux is going to give you the time derivative of the number of people you have inside. This is very simple. And another thing is what is called the production, the inside production. For the people, you cannot except, okay, I will not you cannot produce, or except if you have people dying, for example, in the room. This is a consumption. The production, I let you understand what does that mean. So, it turns out that they use a Gauss-Ostrogradsky theorem. The first part is just the integral of the divergence of the flux that is a flux across the volume, the surface, can be transformed in the volume integral of the divergence of this flux. Okay, this is a mathematical theorem called Gauss-Ostrogradsky, and that was developed in the 19th century, or yes, early 19th. So now, because of these two possibilities, when you look inside, under the integral, you have this equation, which is a general equation for the conservation equation of any quantities. You have that the time derivative of rho A equals minus the divergence of the flux plus a production term. What is a conserved quantity? A conserved quantity is a quantity that has no production or no consumption inside. So the only way to change the value of a conserved quantity in the volume is to change the flux. Okay? And in that case, a conserved scalar A is given by the minus the divergence of the flux. There is no production. This is what we call a conserved quantity. This kind of consideration is also extended to the case of when the scalar is not a scalar, but it's a vector. If the conserved quantity is a vector, the flux is a tensor. That's all. Okay. So you see immediately, you see that the derivative, time derivative, is divergence of a tensor. Okay, let's start with the mass conservation. The mass, by definition, you cannot create or destroy mass, except if you are looking to nuclear physics. In nuclear physics, as you must know, those who have developed a course in physics, that the mass and energy are equivalent by Einstein relation. But this is not our problem. In our problem, we are far from any relativity problem. So the mass is a conserved quantity. You cannot mass. So the mass, the d rho over dt should be equal to the minus divergence of a flux. And this is in fact this flux is in fact the definition of the flow velocity, rho u. This is how to define how do you define the flow velocity? You define by this conservation of mass. Okay. Now it's more it is interesting to introduce the material, or call also the Lagrangian derivative of the convective derivative. There are many names for these things, which is the derivative with respect to time when you follow a fluid particle. So you follow the fluid particle, and in this fluid particle, you try to write what is the evolution, the derivative in time. And this is what is called the time derivative, in which you have two parts. One is the Euler derivative, d over dt, and the other is due to the drift of the flame in a gradient. So you have u grad. So when you use this material derivative, the mass conservation take a much simpler form, telling you that the derivative, Lagrangian derivative or convective derivative of material derivative of density, the relative to the density, is simply the minus the divergence of the flow. So this is, in a sense, this is the how was introduced, how the divergence of a flow was introduced. It was introduced through this mass conservation. You can see that as a definition of the divergence of a flow. Divergence of rho or divergence of the velocity, you have just a change. No, excuse me. Divergence of the density or divergence of the volume per unit mass is just a change of density. So this is. So the Lagrangian derivative of takes this form now, where appear a flux G prime A, which is given by GA minus the convective flux. So in that, for a conserved scalar, you have rho dr over dt, which is minus divergence of what is called the diffusion flux. It is the flux the total flux when you have take out the convective flux. Okay, this is good, but it is not always right. For example, one has to be very careful, and I will be back now to that, to the energy conservation. Because in the energy conservation, what is called G prime here is not only diffusive. It is only the pressure is occurring in it, as I will show you. So one has to be it is a sign to be careful when we are going to look to the total energy conservation and what is the flux involved in the total energy. Fixed law, what time is it? So, okay. When you have a mixture, you introduce the mass fraction, that is a ratio of the mass per unit volume of species I, okay, divided by the density, This is called the mass fraction, and the sum of the mass fraction, by definition, is 1. So in an inert mixture, the mass of every particle is conserved. There is no way there is no production. So in that case, you have that the evolution of the mass fraction should be in the form of divergence of a flux. And this flux is such that the sum of the flux is 0. This is called a diffusive flux. And the kinetic theory of gases show you that it is simply related to the gradient of the concentration through a diffusion coefficient. You see, here immediately you see what is the dimension of a diffusion coefficient. Look to the equation, rho dy over dt equal minus, okay? Now, you have rho on both sides, and now on the left-hand side, you have something which is y divided by a time. On the right-hand side, you have the diffusivity time y divided by a length. Okay, so this tells you what is the diffusion coefficient dimension. So now, if you use a fixed law which tells you how the diffusion flux is related to the gradient of the mass fraction, you put that in the equation and you obtain a diffusion equation for each species when there is no reaction, you know, when there is nothing. So this is a diffusion equation. And here, even here, it's more easy to see what is the dimension of the coefficient diffusion. You know, this on the right, you have diffusion coefficient divided by a length square, because this is a Laplacian, this square of the gradient. So, and on the right side, on the left side, you have 1 y divided by 1 over 2. So it is a length square divided by the time. This keeps you that anywhere. And this is the archetype of irreversible phenomena. So it's time to stop, 15 minutes, and yes?